This conference will now be recorded.
Good evening, students. I hope you are able to hear me and as well as you are hearing the nice background Bengali music. I can't help you guys. You have to compromise with today's this music, background music, because there is a marriage ceremony neighborhood. I requested to at least reduce the sound, otherwise I could not do anything. Anyway, we will be doing numerical problems, so no much distractions, I hope. So we'll be discussing numerical problems from JEE Mains paper 2020, 3rd September. So let us start our discussions. Okay, so the first question says, consider a gas of triatomic molecules. The molecules are assumed to be triangular and made of massless rigid rods whose vertices are occupied by atoms. So you can see this figure. This is a triangle. So triangular molecule having rigid. So it's triangular molecule. So atoms will be like this. Okay, at the vertices. Okay, so atoms will be at the vertices. So like this, if there is a gas of triatomic molecules, okay, and the molecules are made such that these are actually massless rod, kind of massless rod, and all three molecules are attached to the vertices of this triangular shape. Now you have to find out the internal energy of a mole of gas at temperature T. Okay, so you have to find out what is the internal energy. So guys, you know, internal energy you have to find out. And how do we know? So each degrees of freedom, it is actually the law of degrees of freedom. Okay, from there we can find out. So each degrees of freedom will contain half RT or half KT, you can say. So half RT, each degrees of freedom. If I have F degrees of freedom, then the internal energy will be F into half RT. So what is my job here? I have to find out what is degrees of freedom. What is degrees of freedom? Okay, so this is F. Degrees of freedom, we know, you know how many particles are there? 3 particles are there, and this is in 3 dimension. We have to see. Okay, 3 dimension. So 3 into 3 and minus constant number of constants. See, there are constants 1, 2 and 3. There are 3 constants here, so I'll write like this. So what you get 6 independent coordinate or 6 degrees of freedom. Now I'll multiply it here. This F, this is the value of F. So I will have internal energy F into half RT. Okay, half RT. That means what? That means 3 RT. So this is the internal energy. So what is the bottom point here, or what is the point to be noted here? The point is that how many constants are there, how to calculate the degrees of freedom. How to calculate the degrees of freedom? Number of particles into the dimension minus number of constant. Okay, so here there are 3 particles, 3 degrees of freedom because it is in space. Okay, and there are 3 constants. Okay, constant means how many obstructions are there or limiting relationships are there. Okay, that's what we can say in very common language. And this is the expression for the internal energy which I need to remember, that is half RT into the degrees of freedom. Okay, so sometime you might be asked to find out gamma also from this kind of questions. Okay, so once you get U, so you will be able to get CV by making it du dt. So you'll get 3R. Once you get CV, you can find out CP. CP minus CV is equal to R. So Cp minus Cv is equal to R. So Cp will be 3R plus C R. Okay, so this will be 4R, and you have to find out gamma. Gamma is Cp by Cv. So Cp by Cv, gamma is Cp by Cv. So what will be the value? Cp by Cv 4 by 3. It will be around. So gamma will be around 1.33 something. Okay. So this is another question I have discussed now. So this is one question. You have to find out what is the internal energy and how to find out gamma. Also, you can actually remember the process. So once you get internal energy, you can find out Cv from there by just taking derivative with respect to temperature. Okay, and then you can find out Cp minus Cv is equal to R. You know that. From there you will be able to find out Cp, and then you have to take the ratio Cp by Cv. So 4R by 3R. So that will give you 1.33 for a triatomic molecule. All right, let us go to the next problem. And here see one more point. Here actually it was given only for 1 mole. If there is given that n moles, then you have to multiply n also here. Okay, number of moles you have to multiply. The next problem is this one. You look, see this problem says a block of mass 1 kg, a block of mass 1 kg slides with a velocity v is equal to 6 meter per second on a frictionless horizontal surface. So this is frictionless horizontal surface. Okay, there is a block of mass small m which is moving with speed v. Okay, and it collides with a uniform vertical rod and stick to it. See, there was a vertical rod kind of this. As you see in the figure, initially it was like this. Now when the block comes here with the speed v, it actually gets stick to it, and then it take it to some height like this. Okay, it brings like this. All right, so this is the figure, final figure after the block hits the rod, and rod actually moves away from its equilibrium position. Okay, this much it has moved up. Okay, and this is the angle it made. Actually there is a rotational motion since. Okay, one more point here. The rod is pivoted about O. The rod is pivoted about O. That's why there is a rotational motion for this rod along with this mass attached to it after collision. And see what the question says. The rod is pivoted about O and swings as a result of the collision, making an angle theta before momentarily come to rest. Okay, see it will just move up to here, then it comes to rest again. If the rod has mass 2m, sorry, mass m is equal to 2 kg and the length l is equal to 1 kg, the value of theta is approximately what? So there are options: 49 degree, 55 degree, 63 degree, and 69 degree. So guys, you know, here you have to actually consider, this motion as rotational motion. Okay, a rotational motion you have to consider. You know what you can do? You can actually use the law of conservation of linear momentum first, so that you get the final velocity over here. Okay, in fact, I'm sorry, yeah, you can find out the angular velocity with which it is actually rotating. So this is a rotational motion now. So as a whole, you have to consider the rotational motion here now. Okay, first what you have to do, you use conservation law, angular momentum conservation, so that you get the angular velocity with which it is rotating. After you get that, you can find out this angle from there, from the conservation of energy conservation of total energy. Let me tell you what we do here. So first it comes and hit this here, right? So initially this rod did not have any angular momentum, right? Isn't it? So, and we have to actually find out angular momentum with respect to this O pivot. So when it starts motion like this, so at this position after hitting it, there will be some angular momentum, and when it reaches here, so what will be the angular momentum, or with what? So we'll actually use the conservation of angular momentum. And see here the question is, okay, so at any point like this point, it made angle theta, right? So it has certain constant angular velocity. So that I have to find out. Okay, once we find out that, then there is a chance of calculating theta. Let me just do it here. So applying conservation law, of angular momentum. So what is initial angular momentum? So at this position, see, I'll write MVL, right? MVL, isn't it? For this is for the small m mass. I'm calculating angular momentum with respect to O. Okay, but what was the angular momentum? There was no velocity at all with the rod, so there was zero angular momentum initially. But just before it stopped moving further, or when it stops at this angle theta, what is the angular velocity? Let us say that is omega. Here. Okay, just before stopping, anyway, throughout its angular velocity remains constant, isn't it? Angular velocity will be always constant. So this angular velocity throughout this path up to here, the same angular velocity will be there. All right, so in this case, what we can find out, say I can write angular momentum for this, because it has moved with certain angular, it has rotated, right? So that angular momentum for this rod as well as this mass I have to find out. Okay, so anyway, this will be MV, sorry, not V, M, there will be V prime, let us say V prime into L. Okay, and that V prime, if this is V prime is, see, I can write that is L omega, right? If omega is the angular velocity. Okay, so then it will be, see, if I put this L omega, then I get ML square omega. This is the angular momentum for the mass block of mass small m. Then for this I can write I into omega. I is the moment of inertia of the rod. Rod has got mass, it has got certain length, so I will be what I will be, and see, moment of inertia I have to find out with respect to this end. With respect to an end, the moment of inertia will be ml square by 3, isn't it? Ml square by 3. about an end. So I'll put it here. So ml square omega by 3. Sorry, this is conservation of angular momentum. All right. Now I have to find out what is omega. Omega I have to find out. So mvl divided by, see, this is ml square plus ml square by 3. If I do a little bit of simplification, so mvl, I can just strike 1 from here. So this will be L, this will be small m plus capital M by 3. Right? This is fine. So what are m? See, small m is small 1 kg. This v is 6 meter per second. Then I have L is 1 meter, 1 plus 2 by 3. So what I get? I get 18 by 5. This is actually rad per second, radian per second. So you get this omega. So I have got omega. I'll write it here. Okay. Let me see whether I have a page. Yes, I have a page here. Now I can apply conservation of energy. So applying conservation of energy. Conservation of energy. See how we'll apply here. See, initially there was only kinetic energy for this, like it has kinetic energy for both. If I start this as a starting point, kinetic energy for both the rod and this block. When it starts, so it has kinetic energy. Okay, so here I have taken 0 potential energy for the rod. Now when it goes up to certain height, isn't it? Okay, I can find out this L. If this L is, see, this will be actually L cos theta, isn't it? L cos theta. Oh, I'm sorry, this is L cos theta. This is minus L cos theta. In fact, you know, here when I consider mgh, this mass for the rod will be actually see, now you have this combined system, this and this one. So you have to actually find out the RCM, where the total mass small m and capital will be concentrated. Okay, so you have to find out the center of mass for this. Okay, so let me write the conservation law, energy conservation here. See, I can write half mv square for the small mass, so that I can write half m L square omega square, then half I omega square. This I have to write for the kinetic energy for the of the rod. So I can just put the I also. So half I omega square. I we have already found out, that is capital M L square by 3 omega square. Okay, and here you look on the other side. So the whole kinetic energy actually gets converted into potential energy at this particular position, such that it doesn't move further. Okay, so that's why the whole kinetic energy will be actually converted into potential energy. So mgh. Okay, mgh. So what is the height? See, now I have to actually see where this whole mass is concentrated. Now if I take this as RCM, so I have to consider this. Okay, so RCM the whole L cos theta, L minus L cos theta is equal to RCM, isn't it? I'll write it, see, RCM or COM into 1 minus of cos theta. Okay, as we write, see, if it would have been, see here mass is concentrated, so earlier the mass was somewhere R at R, so there I have to consider zero potential energy. Now it has come up to here. Okay, so that is how you have to consider the center of mass. See, when I calculate the potential energy for this rod, I have to consider the mass. See, mgh we write, isn't it? Mgh. So this height we have to carefully consider, because this height is now, see, this is, if this is the position, zero potential position, energy position, so you have to actually think that this is the reference for this rod, because mass is concentrated here. Now when it comes like this, if it is coming here, then center of mass will be actually here, so you have to take this difference as h. Okay, this difference, that is what I am doing here. All right, so mgh, so there will be g as well, so there will be a g also, mg cos theta, so mg into height difference, so that is what I have written. Now if you tell me what is RCM, RCOM, then what I can write, see, I have a rod of length L. You can actually consider that this rod has mass m, right? You can consider two particles now. Okay, two particles. So here one particle and here one particle. So both, say, this guy has mass m, and this guy has some mass, that is capital M. So two particles. I have to consider the, like, I have to calculate the center of mass for these two guys. So how to calculate center of mass? So let us see this thing. This is L by 2, right? If I consider from here, so this has mass here. Okay, so if this is the point of reference, say I can actually take this, say M1 R1, right? M1 R1 plus M2 R2 divided by M1 plus M2, right? M1 plus M2. This is the formula. If I know the positions of the masses, right? So this you take as origin. This you take as origin, so that you get R1 as L by 2 for this rod. Okay. Look, I am writing here then. So RCM is, see, small m plus capital M into RCM. This one will be equal to M L by 2 plus MS. So this is R2 and this mass is M2 and this is R1 from here to here. This is L by 2, and for a rod, center of mass will be obviously at L by 2. So this is what I have written here. Okay, so RCM is what? RCM is M L by 2 plus M L divided by small m plus capital M. So if we just put the values, say, so M is 2 kg, this is L is 1 meter, M small m is 1 kg, this is 1 meter divided by, this will be 3 anyway. So this is giving you, so this will be in meter anyway. So this is half of, so 2 by 3 actually. You will get 2 by 3. 2 by 3, right? So I can just put, so I have got RCM, RCOM as 2 by 3. Okay. So you guys are understanding, I hope. Here this problem is a little difficult, not too much difficult, but mild difficult. Okay, so RCM I have got 2 by 3 RCOM. G is known anyway, so now I can actually take some things common here. See, I can take this L square common, omega square common, then I got small m here, and here capital M by 3. Okay, then this side, you know, this is 1 kg, this is 2 kg, so 3 I can write into this RCM. I have got 2 by 3. G I have to write 10. This is 1 minus cos of theta. One side I have written all the values. No worries, we'll put the values here also. Let me put the value here. So this is 1, this is 2 by 3. M, capital M was 2 kg, so this 2 by 3. So what I get here? This L is 1. Okay, L is 1 kg. Let me keep this omega square here first. So this will be 5 by 2, right? And this side it will be 20, 1 minus of cos theta. Okay, so look here, this is 5 by 4 into omega square means 18 by 5, so 18 by 5 I'll multiply twice, right? So this 20 I can take it to here, this side, 1 minus of cos theta. All right, so this is now this 5 goes up, so I can go with 2, 9 again. Again, this is 9. Let me check. I have done some mistake. No, I hope. Okay, so you have 99, 9 into 9, right? I think I have just done a small mistake. Oh, this is actually 5 by 3, not 2. This is 5 by 3. Okay, so there is, this is 5 by 6, it would be. Okay, then things are all right. This will be 6, so I'll get 1 3 here. So this 3 will strike at one of this 9. Okay, so this is 9 tools. Okay, I think I'll just do the calculations once again. Let me do one thing. I'll write 1 minus cos of theta this side. Then I get here 1 half 5 by 3 into 1 over 20 into 18 by 5, 18 by 5. Okay, now I get this 5 gone, this with 9, this again with 3. Okay, so yes, so one more, this 10 and this is 9. So I get, so 1 minus cos of theta equal to 27 by 50. Okay, so I'll just do a little bit more calculation. So this thing I'll just write them out. You can do in your note step by step. Maybe it is becoming a little bit messy, but anyway, look here, this is becoming this. Okay, so cos of theta will be 1 minus 27 by 50, so that is giving you 23 by 50. And you know, you have to actually guess the values. See here, see cos of theta, when it is, when theta is 60, when, say, I'll just give you the values, then you can actually guess. Actually, you have to guess the values. So when theta has theta has values. Let me write theta here and cos of theta here. I'll just put the known values. When theta is 30 degree, 30 degree actually cos theta root 3 by 2. Okay. When it is 60 degree, it is half. Okay. Before that 45. 45 degree, so 1 by root 2. 60 degree half. So this is here actually 60 degree means 0.5, right? So I should get nearly 0.5 at 60 degree. Look here what we get. So 23, 50. So I can just go with the point. So this will be around 4. So 46, okay, 0.46. The value of this cos theta is nearly equal to 5, nearly 5. And look the questions. So I have 63, 55, 49. So 49 I can strike that out. It will be nearly values of nearly 1 by root 2, near around that. 50 anyway, I have a good guess. See, this is actually nearly 0.5. It should be nearly 0.5 here. Okay, so 63 will be the answer. Okay, I don't know any another way to find out the angles. I don't know. These values are like this, so you have to guess. A wise guess will actually help you here. All right. So next problem. So this problem says the moment of inertia of a cylinder of mass m and length l are about an axis passing through its center and perpendicular to the axis of the cylinder. That means, you know, this is cylinder, right? You have been given the moment of inertia of this cylinder. So this cylinder has length suppose L and mass m. So see, moment of inertia about this axis is given. This is center of mass. So moment of inertia about an axis passing through the center of mass and perpendicular to its axis. Okay, that means this. So I have to actually use here parallel axis theorem, right? So this is moment of inertia about this, like moment of inertia of this disk about this axis diameter. So that is given as m r square by 4 about diameter plus parallel axis theorem, this one, like moment of inertia of this moment of inertia about this uh, end of the rod actually. Okay, ml square, moment of inertia of a rod about an axis passing through its center of mass and perpendicular to its length actually. Okay, so that will be ml square by 12. So this will give you the moment of inertia, so which is given here. If such a cylinder is said to be made, sorry, if such a cylinder is used to be made for a given mass of material, the ratio L by R for it to have minimum possible I. So such kind of material having mass M and length L and with radius R. See, L, I don't know what is the L and R, but if such kind of material is given to make a cylinder to have minimum moment of inertia, where the moment of inertia of this kind of material having, like, if I use to make cylinder of length L and capital R radius, then moment of inertia is becoming like this. So moment of inertia is becoming like this about the center, but I want to have moment of inertia about its center minimum. So then what will be the length by R ratio? That is what is the question. So, you know, to make a moment of any quantity minima, you have to actually take first derivative 0 with respect to the variable, at least with one of the variable. So here actually R and L both may be variable. So first of all, I have to bring this R or L into one among them. So I have to convert R to L so that I get the moment of inertia in terms of L, and then I'll make this dl to be 0. Okay, to make this R to L, convert R to L, there is a relation, say mass is equal to pi R square into L. This is the volume into density. Okay, so this from here, look, I can find out what is R square. R square is m by pi rho and L. So if I put it here, then see what I get. I get this moment of inertia. Let me just erase this figure. I hope you have understood this. So moment of inertia, I'll write it here. I get, see, m will be there, R square. See, in place of R square, I'll put this value. The value will be m by pi rho and L plus this m L square by 12. So these are the things. Now if I take derivative with respect to L, di by dl, look, this will be giving you m square by pi rho L square, and this will be plus m by 6 L, right? If I take derivative with respect to L. Now if I make 0, see, this is the first condition, that if something is maximum or minimum, then I take first derivative and make like make it to 0. All right, then you have to see whether this quantity is going to be maximum or minimum. Here anyway it is given as minimum, it will be minimum only if I take 0. So from here I'll get a relation between L and R. Let me see. So I get m square by pi rho L square, that is equal to ml by 6. ml by 6. So let me do one thing. Let me take this L here. So m square can be, see, I can cancel one m from both sides. This L I can multiply here, so L cube I get here. Now see, this pi rho, if I multiply 1 r square and 1 L here and 1 r square, 1 L here, then what I get, this is also, so this total thing, they will cancel each other because this is also m. Okay, so I get r square L here is equal to L, yes. So I have to take the ratio of L by R. I have, I think, pi r square L, fine, m square by 4. Okay, so this thing I have actually omitted out, this 4. There will be a 4 over here. So this will have, there will be a 4 here. So this is L cube by 6. This is L, 1 L, I can strike them out. Then this will be L square. So see, I have to find out L by R. So L square by R square will be 6 by 4. Okay. So L square, then L by R will be, so this I can strike them out, 3 by 2. So it will be actually root 3 by 2. Okay, this is, yeah, so this is the answer, root 3 by 2. Okay, this was very simple question, but understanding is required. So first of all, you have to understand that you have to somehow make derivative, first derivative 0. But how to make, because there are, see, there are two parameters, one is R, another one is L, and both are variable. Then you have to find out a common relationship by which you can convert one to another, and then you just take a derivative with respect to one variable alone, and then you recall the variable by reconverting it. Okay, so that is what I have done actually here. I hope you have understood. Let us go to the next problem. So this problem says a satellite is moving in a low, nearly circular orbit around the Earth. Low, nearly circular. Low means this circular orbit around the Earth. Suppose this is the Earth. Okay, Earth is radius RE, and this is circular orbit, and low circular orbit means maybe at this position. Okay, so always you know the velocity, linear velocity of this. So this is a satellite which is moving around this Earth. Its radius is roughly equal to the Earth's radius. Okay, Earth radius and the satellite radius of the satellite are both same. Okay, both are same. By firing a rocket attached to it, so with this satellite there is a rocket attached to it, and that is fired. That means its speed will be actually instantly increased. Okay, and increased to, so in the direction of its motion, say in the direction of motion means it is actually moving in this direction now, right? It is moving in this direction. Okay, linear velocity will be at along the tangent direction, right? In a circular orbit, isn't it? If this is the case, you look what happens. Speed along this direction will increase, and this path will be actually somewhat elliptical. Okay, now it is actually the path will be nearly elliptical. Okay, now the path will be nearly elliptical. Okay, now Earth is here somewhere. I would say Earth is here somewhere, because it was when it was at lower point at this particular position, speed was given by firing the rocket. Now it has become nearly, so this is actually this, suppose this is R1. Now since it is elliptical orbit, so it will be having, so this side from the center of the Earth, this side is R1 and this is say R2. Okay, the question is, see, due to this furthest distance from the center of the Earth, that the satellite reaches R. Okay, reaches R. R is actually, say, this R is actually, I'm sorry, this, let us say this is R actually. This is R. This is R. Reaches to R. Okay, it reaches to R from the center of the Earth. And this, let us not take this as R. Both the Earth and this satellite, both of them are having the same radii. Okay, so I'll just repeat the question because the question itself is a confusing question. Once you understand the question, then answer is not too tough. A satellite is moving in a low, nearly circular orbit around the Earth. Its radius is roughly equal to the Earth's radius RE. By firing rockets attached to it, its speed is instantaneously increased in the direction of its motion. So this is the direction of motion. It is actually made now. Earlier, suppose it was having v, okay, orbital velocity v. Now the velocity has become v prime, which is actually root 3 by 2 v. This has been increased to this. Due to this, it will be actually moving this side, and the path will be somewhat elliptical, and say it reaches from the center of the earth, it reaches up to r distance, okay, and from the center of the earth, this is actually from the center of the earth that the satellite reaches up to r. Then you have to find out what is the value of the r, okay. So to do this, what you have to do, you have to do one thing here. You have to uh, remember or recall that the total energy will be conserved, right? Total energy remains conserved, okay. Total energy remains conserved for an elliptical path. How do you write total energy? Suppose this is 2a, okay, that is r1 plus r. This r1 is actually re, okay. All right, so here you look the okay, let me just do one thing. Total energy for an elliptical orbit will be given by minus gm by 2a, and that is the major axis. 2 into semi-major axis, okay. So this is a is the semi-major axis, okay, semi-major axis. All right, so let me write initial energy. So when it was given this much velocity, so what was the energy? It had some potential energy as well as some kinetic energy. What was the potential energy? What was the kinetic energy? I have to write that, okay. So what was the kinetic energy? Half m, half m. Orbital velocity is actually half m v square, right? This v is gm by r, square root of gm by r. Okay, this is gm by root gm by r. Let me write this as smaller. Okay, this smaller, what is this smaller? If this has r, and this center, this earth has radius. Okay, so earth also has re radius. Okay, let me just write it here, half m v square into, see, v has become v prime. That means this will be root 3 by 2. So this also minus gm by r. Okay, minus gmm by r. This will be is equal to gm by 2a. All right. So here, look, this gm, I can strike them out. See gmm. So this small m g. Okay, I can strike them out. Okay, so what I get, 3 by 4 small r here minus 1 by r is equal to minus 1 by 2a. All right. So this r, okay, so this will give you minus 1 by 4r. Okay, this is equal to 1 by 2a. All right. So 2a is equal to 4 small r. Okay, this small r actually I am taking this. Okay, this small r is nothing but r I have taken. Okay, all right. So for r. All right. So now look one thing. 2a is actually, so this much distance. This is the farthest distance I say. This r1 you just leave it here. So this is farthest distance which I have taken as r. Okay, this farthest distance. Okay, plus this much. This will totally constitute your total. It will be actually, look, I'll write it here. So this r plus re, this will actually constitute your 2a. So what this small r is, that is actually re. Okay, because it is nearly on the earth surface. Earth satellite around the earth, I'm just taking this is nearly the earth surface. Okay, so that's why this will be actually small r is actually re. All right, so that is what I have done here. So now I have got this small r to be re, so 4 re, and this r plus re is equal to 2a. So what will be r? 2a means 4 re minus re. So this will be actually 3 re. All right. So guys, you should not be confused with this. See, this I'll just take as, see, if this is a satellite in a low nearly circular orbit, that means it is actually uh, satellite of the earth means we'll just take this radius of this orbit, circular orbit, to be small r only. Sorry, re only. So thus I have the initial kinetic energy according to that. Okay, this r is actually the radius of the orbit, circular orbit, and this is actually the major axis. Okay, major axis. Okay, so major axis will be composed of this small r, the earlier orbit, plus r. This is, so this small r is capital re actually. Okay, I'll just convince you guys, just 1 minute. See, this is the re. Okay, that means the orbit of the satellite is nearly equal to the radius of the earth, because it is just near the earth surface. Okay, it is actually very near to the earth surface. That's what if I just consider. Okay, this was, so then according to this I'll write the initial kinetic energy. So this is the initial kinetic energy, and this is initial potential energy. And then finally what happens when it was here, it has been given certain velocity in this direction, so it has become now electric, like this. Now this is r. Okay, this is r. Earlier it was from the earth center of the earth, it has gone up to r distance, so that is what it is here. Okay, so we know for an elliptic orbit total energy will be gmm by 2a. So this is what is the thing. And see here what I have written, the total energy, kinetic energy plus potential energy at this particular position, and I have written total energy here. So those are the two equal energies. Okay, so what I have written now here, now re plus capital R, which is actually 2a, which I have found to be 4 re. So I have to find out this r. So r is 4 re. 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 4 RE minus RE, so that will be 3R E. Okay, so the option here option A will be the correct answer for this question. Okay, now let us go to the next problem. Oh guys, here I have not written the question. Let me just give you the question here first. Okay, so there is a question here. Suppose there is this using screw gauge of pitch pitch 0.1 centimeter and circular divisions 50, circular divisions 50 on, okay, circular division 50, the thickness of an object measured okay, object is measured. So using object is, okay, thickness of object is measured. So this is the statement using a screw gauge, okay, using a screw gauge of pitch this much and circular division 50, the thickness of an object is measured. It should be directly okay, so it should be nearly okay, it should correctly measure record, okay, correctly be recorded. This question is really a peculiar question, that's why I am just discussing this. The first option is 2.123 centimeter. Option B will be 2.124 centimeter. Option C is 2.125 centimeter, and then option D is 2.121 centimeter. Okay, so I'll just make you understand the question. The question says there is a screw gauge which you are using to measure the thickness of some object. See, specification of the screw gauge is given. Pitch P is given as 0.1 centimeter. Okay, and you have circular divisions, number of divisions N to be 50. Now you have measured the length correctly, okay, and suppose you have got the correct value, but that value, see, is there in between 4 options. So which may be the correct option or correct length you might have got, correct thickness you might have got. Okay, whether it is 2.123, whether it is 2.124, whether it is 2.125 or 2.121. Okay, before I see the options, let me find out what is the least constant here. Least constant is screw pitch by the number of divisions. Okay, so what I get, guys, here, this is centimeter, this is 50, so I'll get something 0.002 centimeter. Okay, so once I get this least constant, from least constant, can you guess something? Yes, one thing I can guess, that the decimal point up to 3 you will have in your answer. So every one of them has this 3 decimal point. And see, any circular reading you get, suppose I get circular reading to be some 20, okay, Then I have to multiply this least constant. Let me just do that and see what I get. I get 4 0. Okay, 4 0, and I have to have here the, okay, so kind of this I'm getting. Look, so if I get some 30, then I'll get 6 over here. If I get any number, some 19, I'll get 18 here. That means, you know, the last decimal you must have, the last decimal you must have the even number. The even number, the last decimal you must be having an even number. Okay, at least see, you see from here which one has the last decimal even number. You'll get the last decimal even number, that is for sure. So because your this constant is 0.2, and see these decimal points will be, last two decimal point will be due to the screw gauge. Okay, last two decimal point will be actually coming from your screw gauge, and see screw gauge will give you the circular reading. Main reading anyway you will get it in 2 point something, 3 point something, 1 point something, but last two decimals will be obtained from the screw circular reading, and you have to multiply this concept with each and every circular reading, and that will be found to be even number. So as a whole you should get actually even number. The last two digits you should have an even number. Okay, because of this list concept. So option B will be the correct answer for this question. Guys, I'll go for another question at least. Let me give you the question. There is a nice question here. Okay, so there is a very nice question that I am going to tell you now. See, pressure inside two soap bubbles. Pressure inside two soap bubbles are respectively two soap bubbles are given. Soap bubbles are respectively 1.01, okay, and 1.02 atmospheric pressure. Okay, okay, the ratio of their radii will be, options are 0.8:1, option B is 2:1, option C is 4:1, and option D is 8:1. Okay, so here see, we know the expression for excess pressure, right? Excess pressure. Excess pressure for a soap bubble, we know delta P is equal to 4T by R. Okay, this will come into work. So from this expression, what we can write? See, this pressure is actually the gauge. I see this is actually gauge pressure, but the pressure here is given only the inside. Pressure inside is given. So how do you get the gauge pressure? So this is actually a gauge pressure, okay? Gauge pressure. So gauge pressure is actually, you know what is gauge pressure? So pressure, absolute pressure minus atmospheric pressure. Atmospheric pressure. This will give you the gauge pressure, okay? So which is like this formula. Excess pressure is the formula with the gauge pressure. So what is given here? The pressure inside is given, or absolute pressures are given for the two soap bubble. This is where the point is. Actually, you guys will do the mistake here only. You'll directly put this here in place of delta P and then do the things, but that is not correct. You will now look what I'll do. Delta P1 by delta P2. This is 1 over R1. This is R2. The rest of the things will be cancelling each other. So this delta P1, look what I'll write. Delta P1. This is actually pressure inside minus atmospheric pressure. Atmospheric pressure, let us take that as 1, and this pressure inside is 1. Okay, atmospheric pressure is 1 atmosphere. So this is atmosphere. So this is 0.1 atmosphere. Okay, guys. Similarly, delta P2, you will get 1.02 minus 1, which is 0.02 atmosphere. Okay, atmospheric pressure. Now you will be able to find out. So this is 0.01 divided by this is R2 by R1. Okay, you have to find out. I guess this is not ready. Their volume. Okay, I'm sorry. This is ratio of their volume. Okay, volume. So I get R1 by R2 is equal to 2 by 1. Okay, then what will be the volume ratio of the volumes? V2 by V1, that will be 8 by 1 or 8:1. Okay, this is the answer. So where was the point? Point is that the formula for excess pressure we know is the gauge pressure. Okay, this is the excess pressure. Okay, gauge pressure. That is where the point was. Otherwise, things are okay. So I think I'll stop it here for today. In the next class, we'll continue with this 3rd September JEE main paper in the next classes as well. So thank you for your patience. Bye for today.